Welcome back, everyone. Ready to dive into a topic that's all about uncovering hidden connections.
You bet. We're talking about regression analysis today. It's all about finding those sometimes sneaky relationships in our data.
So, if I wanted to prove that eating more pizza leads to better dance moves, could regression help me with that?
Well, maybe not that specifically, but you're getting the idea. Regression is about figuring out how different factors relate to each other, whether it's pizza and dancing or something a bit more scientific.
All right, so maybe I'll hold off on that pizza study for now. But seriously, when we talk about relationships in data, what kinds of things are we looking for?
We're searching for patterns, trends,
Hmm.
ways to understand how one thing might influence another. Like, how does the amount of rainfall affect crop yields, or how does the time spent studying relate to exam scores?
Okay, so it's about finding those aha moments where we can see a connection between things.
Exactly. And those insights can be incredibly powerful. They help us make better decisions, predictions, all sorts of things.
So regression analysis is like having a superpower for understanding data, right?
You could say that. And like any good superpower, regression comes in different flavors. We've got linear regression, and then there's nonlinear regression.
Ooh, that sounds intriguing. Linear regression, does that have something to do with straight lines? Like from math class?
You're right on the money. If you can picture plotting your data points on a graph and drawing a straight line that captures the general trend, well, that's linear regression in action.
Ah, now it's all coming back to me. Y equals mx plus b or something like that.
You got it. But we won't get too bogged down in the formulas. It's more about understanding the concept. Like, imagine you're looking at the relationship between years of experience and salary. Often, the more experience you have, the higher your salary. And that could be represented with a straight line.
Okay, so a simple, straightforward relationship. That's where linear regression shines. But I have a feeling things are about to get a bit more complex.
You read my mind. Because not everything in the real world follows a nice, neat, straight line, right?
Definitely not. Think about things like population growth or the spread of, let's say, a viral video. Those things don't exactly move in a straight line.
Precisely. That's where nonlinear regression steps in, when we're dealing with curves and more intricate patterns.
So instead of a ruler, we need something more flexible, something that can handle those twists and turns in the data.
Exactly. And that means we need to bring in some different mathematical tools, things like exponential functions, logarithmic functions, and a whole bunch of others.
Okay, so things are getting a bit more advanced. But hold on, before we get too deep into the mathematical weeds, can we take a step back and just clarify the core difference between linear and nonlinear regression? Like, how would you explain it to someone who's completely new to all this?
Well, I'd probably say that linear regression is about finding the straight line that best fits the data, while nonlinear regression is like, well, imagine trying to draw a curve that follows the data points even when they're not in a straight line.
I like that. It's like the difference between drawing a basic sketch and creating a detailed, maybe a sculpture.
Exactly. And the choice of which approach to use depends on the nature of the relationship we're trying to understand. Straight lines versus curves, simple versus complex. It all comes down to what the data is telling us.
It seems like that first step of visualizing the data is crucial. You need to see what you're working with before you can decide whether to grab the linear or nonlinear toolkit.
You got it. That visual step helps us determine which approach is going to give us the most accurate and meaningful insights. So we're pretty clear on linear regression, but when we hit those more complex relationships, that's where nonlinear regression comes in.
It's like we're taking our data analysis skills to the next level, trading in our straight lines for something with a bit more curve appeal.
I like that analogy. And knowing when to use each approach, that's where the real magic happens. It can make a huge difference in how we interpret and use our data.
So give me an example. When would you absolutely need to ditch the straight lines and go full-on curvy?
Well, imagine you're tracking the adoption of a new technology over time, like how many people are using smartphones. In the beginning, it might be slow going, then boom, it takes off like a rocket, and eventually it kind of levels out as most people who want one have one.
That classic S-shaped curve. I remember seeing that in my economics class.
Exactly. And you can't really capture that with a simple straight line. You need a nonlinear model to really understand those different phases of growth.
Okay, so nonlinear regression helps us see those turning points, the moments where things speed up, slow down, or even change direction.
You got it. It's like having a more powerful lens to zoom in on those intricate details. Let's say you're studying the effects of a new medication. At low doses, the relationship between the dose and the effect might be linear, but at higher doses, it could plateau or even become harmful.
Whoa. So in that case, sticking with a linear model could miss those critical shifts in the relationship. It's like trying to navigate a winding road with a map that only shows straight lines.
You're exactly right. And when it comes to making predictions, those nuances can make all the difference.
Speaking of predictions, I can see how a linear model would give you a straightforward forecast. But how do you predict with those curvy nonlinear models?
It definitely gets a bit more complicated, but the basic idea is that we're fitting a mathematical function to the data, a function that can accommodate those bends and twists. And that function allows us to extend our predictions beyond the data we already have.
So instead of just extending a straight line, you're kind of extending that curve, following its path into the unknown.
Precisely. But of course, with greater flexibility comes greater responsibility. We have to be extra careful with nonlinear models because they can be more sensitive to outliers or unusual data points.
So it's kind of a trade-off. You get more power, but you also have to be more mindful of the potential pitfalls.
Exactly. And that's why it's so important to choose the right tool for the job, to understand the strengths and weaknesses of each approach.
So it's not about linear versus nonlinear. It's about knowing when each one shines brightest.
Absolutely. And sometimes the best solution might even involve blending elements of both approaches.
Oh, really? Hybrid approach. I'm intrigued.
Think about it. Let's say you're analyzing the relationship between air temperature and energy consumption. During those mild spring and fall days, the relationship might be pretty linear, but as temperatures get super hot or super cold, energy use could spike dramatically.
So you might have a straight line for the middle part of the data, but need some curves to capture those extreme temperature effects.
Exactly. In those cases, we can use something called a piecewise function, which basically combines different segments, some linear, some nonlinear, to create a model that accurately reflects the overall relationship.
So it's like building a model with different Lego blocks, snapping together those linear and nonlinear pieces to create a more complete picture.
I love that analogy. It really highlights the flexibility and creativity that we often need to bring to data analysis.
Well, this has been a fascinating journey into the world of nonlinear regression. We've seen how it helps us understand those complex relationships and make more accurate predictions.
And I hope we've shown that while it can be a bit more challenging, it's definitely worth the effort.
Absolutely. I think our listeners are now equipped to spot those curves in their own data and maybe even start thinking about how they could apply nonlinear regression to their own analytical challenges. We've covered a lot of ground talking about the strengths of both linear and nonlinear regression, but I'm curious, are there any potential downsides? Anything we should watch out for?
Yeah, definitely. And one of the biggest pitfalls is something we call overfitting.
Overfitting. Okay, that sounds a little intimidating. What exactly does that mean?
Well, imagine you're trying to, let's say, tailor a suit, and you get it to fit the measurements perfectly, but it's so tight you can barely move. That's kind of what happens with overfitting.
So the model's super focused on the data it was trained on. It's almost like it's memorized the answers instead of understanding the material.
Exactly. And while it might look great on the training data, when you try to apply it to new data, well, it just doesn't work. It's like trying to wear that super fitted suit to a different event. It's just not going to fit right.
Okay, I get it. So how do we avoid falling into that overfitting trap?
One way is to keep our models as simple as possible. The more complex the model, the more likely it is to latch onto those tiny random quirks in the data that might just be noise.
So simplicity is key. It's kind of like choosing a classic, well-tailored suit that'll look good no matter what.
Right. Another technique is something called cross-validation. Imagine you're trying out a new recipe. Instead of just making it once, you try it multiple times with slight variations to see how consistent the results are.
So you're basically testing the model on different sets of data, making sure it can handle a variety of situations, not just the specific data it was trained on.
Precisely. And that helps us avoid those overly fitted models that fall apart when they encounter something new. And finally, it's super important to understand the assumptions behind each type of regression. Both linear and nonlinear regression make certain assumptions about the data, and if those assumptions aren't met, well, your results might not be reliable.
It's like trying to bake a cake without following the recipe. You might end up with something, but it's not going to be what you expected.
Exactly. So it's always a good idea to check those assumptions before you jump into your analysis. Make sure you're using the right tool for the job.
Well said. It's been an amazing journey exploring the world of linear and nonlinear regression. We've learned about their strengths, uncovered some potential pitfalls, and even seen how these techniques can be applied in creative ways.
I hope our listeners are feeling inspired to take a closer look at the data in their own lives. Who knows what hidden connections they might find?
Exactly. Remember, with the right tools and a little bit of curiosity, anyone can uncover fascinating insights. And that's what makes data analysis so exciting. So until next time, keep exploring and keep asking questions.
And never stop learning.
That's a wrap for today's deep dive into the world of regression analysis. Thanks for joining us, and we'll catch you next time for another adventure in data.